My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and very good afternoon to all those who are watching this program live from UK. So hope you are well and safe from Corona pandemic. So as we know that we are staying in a Corona pandemic situation, and the situation becoming worse day by day. So we have to follow our health rule. So I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. We have successfully completed our 222 international physics webinar. Today it's our 223rd international physics webinar. And today we would like to welcome you all to a joint session between our Department of Physics, Pabna University of Science and Technology, and the Department of Physics at Durham University, UK. We have with us here today Dr. Charles Stuart Adams, Sir, Professor, Department of Physics, Durham University. He has already connected with us, so I'd like to welcome our speakers. Good afternoon, and thanks for joining with us, and thanks for giving us this opportunity to attend such an important webinar. So before going to you, I'd like to introduce you with our student. So dear student and viewers, I think you have already come to know that the title of this today International Physics webinar title is the Quantum Semiotics, and I think you will enjoy this very exciting topics. And our speaker is Dr. Charles Stuart Adams, Professor, Department of Physics, Durham University. And we can see that our speaker, Dr. Adams, Charles Adams, has completed his PhD from Glasgow, and then he completed his postdoc from Constance and Stanford, and he also working as the director of the Joint Quantum Center, Durham and Newcastle, and head of the Quantum Light and Matter Group at Durham University. His research specialization is quantum optics using the atomic system, and he's a pioneer of the field of Rydberg quantum optics. So it's my honor to host him in our webinar. So he was awarded the Thomson Medal of the Institute of Physics in 2014 and Holwick Prize Awards jointly by the Society of France Physical Society at and the IOP in 2020. So I think you will enjoy this session. So thanks again, sir, for accepting our invitation. It's your time, sir. You can start your session.
So thanks very much, Pretam, for this invitation. It's my first time to give a talk, albeit virtual, in Bangladesh, so I was very excited about that and very excited to learn about...
welcome our country.
Yeah, thank you.
Hopefully after the COVID, we will invite you for a face-to-face session to visit our beautiful country.
Yeah. Okay, so today I'm going to talk to you. It's actually a completely new talk. So I made a new talk on this quantum semiotics, which is probably something you haven't heard of before. So I'm going to tell you what it is and why I'm interested in it. And hopefully I can get some other people interested as well. So I'll just give a bit of background on myself and where I'm from. So this is a map of a population map of England. So the dark bits are the dense bits. So you see London down here, and then we're right up in the north here in Durham. So this is a very beautiful place with very old cathedral. And currently, because of lockdown, I'm actually in my house, which is out in this region here where there are very few people. So I'm kind of lucky to be able to stay away from big crowds, let's say. And this is just a nice photograph from near where I live. So that's where I am. And then in terms of what I do, so as a professor, I do research and teaching. So as Pretam mentioned, my main research area is in quantum optics, and in particular using Rydberg atoms, but also more standard atoms. And if you're interested in that, you can read some of these works on our Rydberg activity. So we wrote with my colleague Nicola Siblich, we wrote a book, interactive book on Rydberg physics a few years ago. And this is one of our most recent papers where we're looking at making qubits. So I'll talk a bit today about qubits and Rydbergs and how we put them together. And also we're doing a lot of work on sensing with Rydberg atoms. And this is a nice paper where we do some terahertz imaging with Rydberg atoms. So that's kind of the range of topics that I work on, mostly experimental. Now, in addition to research, obviously I do teaching. So I've been teaching for over 25 years now, which means thousands of people, maybe 4,000 undergraduates have had to suffer my lectures. So some of the main areas I've been teaching in are in optics, and with a colleague, we wrote a book on optics a couple of years ago. And also we do a lot of experiments with our undergraduates where we develop some of the ideas and publish them in journals such as American Journal of Physics. And those are experiments that are not too demanding in terms of equipment and things, and can be done in many institutes around the world. Now, the other area I've been teaching is in quantum physics. So back in around 2004, I started a new course for our final year undergraduates, which was on, it was called Atoms, Photons, and Qubits in those days. So it kind of introduced this new idea that was up and coming about quantum computing and qubits. And you can see these were my original set of notes from back in those days. And if you look here, you can see that in the title, our goal was to build a quantum computer based on trapped atoms or ions. So that was kind of the theme of the course. And in those days, it was really something that we weren't really sure that it would be possible. And really, the world has moved on quite dramatically since then. And we now have many companies around the world working on quantum computers with many, many different systems. So the course was evolved a little bit. I'm now teaching it again. It's changed names. And really, some of the ideas I'm going to talk about today really come out of the teaching about how to teach quantum and what are the issues involved there, because it's actually quite demanding to understand some aspects of quantum mechanics, and I'll touch on those issues as we go through the talk. Okay, so this is an outline of the talk, quantum semiotics. So I'm going to say, what is the problem that I'm trying to address? What is semiotics? Now, I'll spend a bit of time on that because you may not be familiar with it. I didn't actually know what the term meant until earlier this year. So I'll explain what I mean by that. And then what is quantum semiotics? I'll explain what I mean by that. And then finally, I'll present some examples of what I think are quantum semiotics, so that they help us solve this problem, which I'm going to now introduce. So the best way of telling you what the problem is to go to one of the masters, Richard Feynman. So my favorite Feynman lecture are these messenger lectures that he gave in 1964. They were given at Cornell, I think. And I think this was one in the series. It was called Probability and Certainty, the Quantum Mechanical View of Nature. And this is where he made one of the most famous quotes from Feynman. I'll play it to you in the video. So it's...
On the other hand, I think I can safely say that nobody understands quantum mechanics.
Oh, I've gone and played it again. Never mind. I'll stop that there. So Feynman said that I can safely say that nobody understands quantum mechanics. So it's partly a joke, but actually it's also serious. And many other famous pioneers in quantum physics have also said that Bohr said that if you think you understand quantum mechanics, then you don't. So we really have a problem to understand certain aspects of quantum physics. And the thing I've always struggled with when I teach quantum mechanics is I think, well, if Feynman doesn't understand it and Bohr doesn't understand it, what hope do I have and what hope do my students have? And how should we sort of go about tackling that? And what kind of tools can we use to make that easier, to develop this understanding? And that's where I think this quantum semiotics comes in, as you'll see. So if you follow the whole lecture, and I do recommend this whole lecture, there's a bit further on, which is my favorite little piece of Feynman. I don't completely agree with what Feynman says here, because he then goes on to say, okay, we don't understand it, but don't worry about it. Don't worry that you don't understand it. So if you just listen to this clip.
Don't keep saying to yourself if you can possibly avoid it, but how can it be like that? Because you get down a drain, you get down into a blank blind alley of which nobody has yet escaped. Nobody knows how it can be like that.
So Feynman says, don't worry if you don't understand it, or worry about why is quantum mechanics so weird? Why is this quantum world so bizarre? He says, don't worry about that. But actually, I can't help worrying about it. And I sort of feel we should worry about it. I think he's advising people not to worry, because you get hung up on that point and then you can't move forward. But I think that maybe it's our job as teachers to worry about it and to think, okay, what is there some better way that we can explain this? Is there some better way that we can understand it? And that's what I'm trying to address in this talk. So I would say Feynman says you'll get down a drain and nobody's yet escaped, and that describes my life. I've been in the drain. I have not yet escaped, and quantum semiotics is my last hope of getting out. So that's what this talk is going to be about. All right. So I talked about optics, and I taught optics a lot. Optics is great because you can see it. So you can go into the lecture theatre and you can make demonstrations with lasers. You can demonstrate Young's double slit. You can do all this wonderful stuff. But when it comes to quantum, you can't really do anything. You can't show people quantum. You can't show people a superposition, a quantum superposition of Schrodinger's cat being dead and alive. We can't see that. We can't see quantum. So when it comes to quantum computing, we can see this very easily by talking about the classical bit versus the quantum bit, or qubit. So the classical bit has two states, 0 or 1. And the difference with the quantum bit is it can be 0 or 1, or 0 and 1. So it can be both at the same time, but it's only both at the same time if we do not look. Because when we look, we just see 0 or 1 again, and we're back in the classical world. So we destroy this quantumness if we look. And my collaborator on a lot of this work and a lot of the figures in this talk, Nicholas Sibulich, put it very nicely, I think. And he said, well, basically, if you can see it, then it's not quantum. So that's really our problem that we have when we try to understand quantum mechanics, that we can't see it in the same way as we're used to seeing optics and we're used to seeing the outside world when we go out on the street. So that's what we're going to try and address. So part 2 of the talk then is going to be talking about what is semiotics, and just in the broad context. So this is an old field. There are some people that work on this exclusively, but it's not talked so much about in physics. So I'll just introduce the basic idea. So the word was introduced by John Locke, who was a philosopher in England a long time ago. And he basically defined it as the doctrine of signs, or we could say symbols. So it's about how we try to represent the world, how we try to understand the world using signs and symbols. So I've just got a few examples that I'm going to run through very quickly, where we use signs and symbols. So they're so common that we hardly ever talk about them. So obviously there is language where we use different types of alphabets. We have things like maps. And you have to learn about maps. So if you've never seen a map, you wouldn't really know how to interpret these pictures. But most of us learn about maps, and then we kind of understand. And whether you're seeing a map of near where I live or of Bangladesh, then you kind of understand that this blue line is a river, and you understand which things are towns, and you understand which things are roads. And so we get familiar with these signs and symbols and how to interpret them. And this becomes a very useful tool in order to navigate through our lives, let's say. Now, in the 20th century, we had computing appeared, and computing has its own sort of semiotics, its own set of signs and symbols. So you might say they are code, but code's written in alphabets and equations and mathematics. There are also other forms of of signs and symbols that are, so this is how people used to write code with these computer punch cards. So if you look at that, you've got no idea what it means, but for someone that was a programmer using a punch card, they could probably understand what that did. And here's another example, much more recent now, of a programming language introduced by Brett Victor. And this is called Dynamic Land. And basically all their programs are written in terms of these colored dots. So you see these colored dots on the table, and then they're read by a camera from above, and then something happens. So it's a very, very different way of thinking about how to interact with the world, here by holes and here by colored dots. So this is some of the idea that gets us into a more abstract space of semiotics. Now let's come to physics. So we're all familiar with this kind of stuff in physics, that we generally use maths and mathematical symbols. I have to have Maxwell's equations there. So in my own story about how I became fascinated by physics, somebody gave me a book on electromagnetism, which was it was too advanced for me at the time. I didn't understand any of it, but it had the Maxwell equations in. And I was so intrigued that I wanted to understand that language. So a goal for me was to work out, what does this strange stuff mean? And that's a bit sort of why I started on a physics journey. So again, it's about interpreting these signs and symbols and knowing what they really mean. So in physics, mathematics is clearly our leading tool that we use to do physics. But it's not the only tool, and that's what I want to emphasize in this talk, that there are other signs and symbols we can use. And we could look back to Leonardo for inspiration, because Leonardo clearly was known as an artist, but he was also a scientist and inventor. And the interesting thing about Leonardo is he did his science, let's say, not with mathematics, but with pictures. So these are some of the sketches, the famous sketches by Leonardo, where he shows us understanding certain phenomena like optical phenomena. So this is this cardioid that you see when light is reflected from a curved surface that you can see inside a cup when the sun shines on your drink. Things like shadows, and this was something that Leonardo invented, actually, this cog, this gear. Slanted gear system, and he understood topology, he understood geometry, and that allowed him to invent without the sort of way that we go about inventing ideas in physics, purely with mathematics. So the question we'd like to ask is, can I think diagrammatically? You could call this a diagrammatic reasoning as opposed to a mathematical reasoning. And is there something we can do in quantum mechanics that would be a diagrammatic reasoning, and it allow us to gain a deeper understanding and advance our interpretation of the world and our knowledge? And that's really what I'm calling quantum semiotics. So is there some symbols, some signs, some diagrams that help us to advance our understanding of quantum mechanics, and hence things such as quantum computing, etc. Okay, so moving forward a little bit now into the modern era in physics, there's a very nice sort of summary of what I'm talking about from Heinrich Hertz. So this book was published posthumously, actually, called The Principle of Mechanics. But right at the beginning of this book, he summarizes what I think I'm trying to achieve, is that he says, we form for ourselves images or symbols of external objects. So that's exactly what I would call semiotics. These images, symbols, are representations of the reality, but they're kind of simplifications. And then he says one image may be more suitable for one purpose and another image for not. So there isn't necessarily a unique symbol, so we might say that equations was one type of symbol or image, and some diagrammatic or schematic was another type, and both, they can complement one another in some way. Now, what I find fascinating about this is it kind of almost seems to anticipate the 20th century and the birth of quantum mechanics. Because if you move forward now some years to the 1920s and 30s, then we have the birth of quantum mechanics, and really everything changes, because now we were talking about things that don't fit our classical description. So the classic example of this is wave-particle duality that was invented by Bruy. Now, what wave-particle duality told us is that things like a photon, it can be a particle or a wave, and it can be both. And if we ask it, "Are you a particle?" it says, "Yes, I'm a particle. I'm a photon." If you ask the wave question, if you do an experiment to measure its wave properties, you say, "Can you interfere?" It says, "Yes, I can interfere like a wave." So it's both a particle and a wave. And actually, de Broglie he summarized this very nicely. So he said that we can understand these descriptions as certainly complementary, but at the same time, strictly incompatible. So classically, in terms of like with the way we've interpreted the world for millions of years, something can't be both particle and wave. It has to be sort of one or the other. And yet now we have this thing that can be both. So somehow these things are strictly incompatible. And then what de Broglie said to sort of reconcile this conflict, he said, was that these complementary descriptions are sort of an idealization. So they're not the whole story anymore. We can't see the true quantum nature of things. We can only see aspects of it. So they allow us to see certain aspects, but not all aspects. So we can't see everything at the same time. So somehow our knowledge of these quantum systems is limited. And I often when I talk about complementarity and wave-particle duality, I often like to use these pictures of Escher, where here you see either you see the white vase or you see the faces, but it's very hard to see both at the same time. So I think that's a nice image or diagrammatic illustration of what de Broglie and wave-particle duality is getting at here. Okay, so let's now zoom through the 20th century and come right up to the current day. So there's a lot of excitement globally now about quantum computing. So not only have we got quantum mechanics and we begin to understand it, although of course nobody understands it, as Feynman told us, but now we're starting to use it. So it's kind of disturbing that we have this thing that nobody completely understands, but it's useful, and we want to build stuff. We want to build quantum technology, and this is growing very, very fast. So there are many people working on these quantum technologies, and how to understand what's going on, and then how to teach things like quantum computing. So in quantum computing, we have circuits, we have quantum gates, and then if you look at how people try to represent these things, this is the sort of diagram of where you can go on the computer and simulate a quantum computer with these circuits and gates, and then you get some kind of output, and you can see they're quite complicated. So there are things like there are spheres, there are circles with lines in, there are different colors, and that's one example that was from Craig Gibney at Google. This is an example that IBM have created. It's called Qiskit. So you can go to the IBM quantum experience and you can build up quantum circuits. And again, now there are spheres. So they call this thing the Q sphere. There are different colors. There are histograms of things. So it's all quite complicated and abstract, I would say, in some ways. And so I'm going to talk a bit about how have we ended up with these pictures or this type, and what's the best lead into this, or is this the best? So this is very specific to, say, quantum computing. But if I take a step back and say, let's just understand quantum systems, not specifically try to build a quantum circuit, but let's take a step back from going that far and just look at simple quantum systems and try to understand those. Okay, so taking that step back, then the basic building block that we have in our quantum system is what we would call a qubit. And I said earlier on how this qubit, so it has two states, 0 and 1, just like a classical bit. But now the new bit is it can be in both states 0 and 1 at the same time. And the probabilities of being in 0 and 1 are given by a squared and b squared in this quantum superposition. So in terms of quantum mechanics, we write this thing as this superposition of being in 0 and 1. And so that's called a two-state system. So these things have been around. So things like a spin 1/2, you know, a spin 1/2 electron has a similar thing. It can be in a state spin up, spin down. A photon can be in a state of left polarization or right polarization. So there are many, many examples of these two-state systems, and we've known about them a long time. So a lot of this mathematics is well developed. And a lot of the people that looked at this earlier on were people like Bloch and Rabi, and they developed a lot of the formalism. So the idea that Bloch had, and it actually built on an earlier idea of a Poincaré, was to represent this state of our qubit using what's called the Bloch sphere. So I can basically write these coefficients in terms of angles, so cos theta and sine theta, and some additional phase, and then this theta and phi become the coordinate in spherical polar coordinates. They become a point on the sphere, and that sphere is called the Bloch sphere. So now the state of my qubit is represented by a Bloch vector, which is this blue vector here. And I can do things like dynamics. So I can solve the Schrödinger equation, and I can, in quantum computing, I can do things like single qubit gates by rotating this Bloch vector. And we rotate about some given axis. So here I've shown a rotation about this axis here, which is in my picture, it's supposed to be the x-axis. So this vector, we can think of this as like a torque. So I do a rotation around this torque vector, this yellow vector, and this yellow vector can point in any particular direction. Now we can define that direction using real world parameters. So when it comes to, like, I want to really have one of these qubits and I want to do one of these single qubit rotations, how do I do it? Well, I take something that has two energy levels. So it could be an atom, it could be an ion, it could be one of these superconducting circuits. And then I apply a field, an external field, an electromagnetic field that drives the population between these two states, 0 and 1. And then I have various parameters like the amplitude of the field, the phase of the field, and also the frequency of the field. So these three parameters define this torque vector. So I can map each of these three nx, ny, nz, the components of the torque vector, onto these parameters. So this thing omega is known as a Rabi frequency, and that is proportional to this amplitude. Then this phase appears in the torque vector components, and also the frequency appears via this detuning of my electromagnetic field from the resonance, the energy difference between the two atoms. So basically, using the parameters in the experiment, we can choose that torque vector in any direction. So let me show you an example now. So hopefully this is going to work. So here I'm going to show an example. So there's my torque vector, and then I'm going to try and rotate now. So over time, if I just watch what happens, so if essentially I'm applying a laser to my qubit, and then we can see this thing just rotate in time like this. And you can see what happens is I start in 0, I go to 1 at the bottom here, and then I come back to 0. And if I carried on for more time, I would keep oscillating between 0 and 1. And these oscillations are known as Rabi oscillations. So normally, if you want to do something like a gate, then what you would do is you would stop at some point. So say you want to do a NOT gate, you want to turn your 0 into a 1, you would just basically turn off your laser here when you get to the bottom, and then you've converted your 0 to a 1, and that's a NOT operation. Now, the nice thing in this model, I'm not going to talk a lot about this, but I'll just mention it, is that we can also add imperfections about how this block vector changes if we have interactions with the environment. So these processes are often referred to as decay or decoherence. So if I just basically run the thing to the end, and now I add a decay, you can see what happens is this block vector shrinks, so it starts to collapse towards the center. So I'm basically losing probability to be in one state or the other. And that's a kind of error, if you like, in your quantum computer. So this block sphere is very nice. So I could say I've spent many years in teaching quantum stuff, in trying to make the perfect block sphere, and this is as far as I got so far. Now, so what's the problem? So part of this section is what's the problem. So I just wanted to show you a couple of tweets that people wrote about the block sphere just from last year. So this was August last year. I don't want to pick on these people. They've got a reasonable viewpoint, which I'm going to pick up on. So somebody says, I don't like the block sphere. It's a limited analogy. You just need to unlearn it to understand anything more than 1 qubit. And then somebody replied, actually, this is a guy from IBM. He said, bad quantum computing teaching philosophy, which is basically just what we've done. This is a qubit. This is how to visualize it on the block sphere. And now you probably need more than 1 qubit. It's good. And then he says, block spheres don't work anymore. Good luck doing that. So is this not the way to teach quantum computing? So that's the question. So the thing I want to try and address is to help you understand what's the problem with the block sphere now that we've introduced it, and then also what would we do if we want to go beyond it? So what would be the answer to that? So that's going to be the sort of next step of this seminar. So as they said in that blog, as soon as you go in that Twitter post, as soon as you go beyond 1 qubit, you get into problems. So I'm now going to say, let's consider if we have 2 qubits. So before we just had the possibility I could be in a 0 or a 1. And now when I have 2 qubits, I have 4 possibilities. So I could have both in 0, both in 1, 1 in 0, 1 in 1, and 1 in 1, 1 in 0, like that. So I have 4 possible terms in my superposition. And they say, oh, well, everything's fine. That's okay. Now, these coefficients are all independent of one another. So what John Bell recognized was that you can have some very odd states. And they're now called Bell states. So in a Bell state, I end up in so these 2 terms, so in this one here, this one called phi, capital Phi, these 2 terms are 0. And then everything is in. So here I'm in a superposition of either both qubits being in 0 or both being in 1. So that's one type of Bell state. Or I have the opposite, where 1 is in 0, 1's in 1, and the other way around. So I've got this superposition of them being in the opposite states. And these are known as Bell states. And they're what's called maximally entangled states. So these are entangled states of the atom, because there's a perfect correlation between the 2 qubits now. So here, if I detect 1 qubit in 0, then I know the other one's in 0. Or if I see it in 1, then I know the other one's in 1. But I could be in the superposition of these 2 possibilities. So there's a complete correlation between these 2 qubits. They're sort of joined at the hip, so to speak, and that kind of changes everything. Now, at first you might think, well, these are just a curiosity, but now they're a reality. So we actually have many ways now of making these Bell states. They're relatively easy, and they're being made probably every day as we speak. People are making Bell states and using Bell states in different ways. And not only are they sort of essential for the power of quantum computing, but they're also used in things like quantum cryptographic systems. So you can make Bell pairs with photons, and then you can send these photons off in different directions, and those correlations survive over long distances, and you can use that for quantum cryptography to make very secure networks. And now, just this year, in fact, in China, they've been doing quantum cryptography via satellites. So they have enormous quantum cryptographic networks spanning thousands of kilometers. So these Bell states are really a practical reality that we're using, and we have a problem to understand them. So what's the problem with the block sphere now? So let me try and show this, and there'll be a little bit of maths here. There's not much maths in my talk, but here there's a little bit. So I showed you earlier on how if we want to do a qubit rotation, we describe that with a rotation matrix, and we can derive the matrices to rotate around particular directions. So here I'm doing a torque vector along the y-axis, and I want to do a rotation, and it's a nice simple matrix. It just has some sines and cosines. Now, if I want to rotate both qubits now, so I'm going to apply this same rotation to both qubits. So I just need 2 Bloch spheres, or do I? Can I just take my Bloch sphere times 2 and then do this rotation, and I'm all done? So let's write down the mathematics for this. So if I want to do the rotation now on the 2 qubit system, I do what's called a tensor product of these two rotation matrices, and then I get a 4x4 matrix. And that's good because remember my state had 4 possible turns in the superposition. So now I apply this 4x4 matrix to my state vector, which has 4 terms. So that's here. And I'm going to choose one of the Bell states. So I'll choose this phi plus. Remember, phi plus was a 0, 0 plus 1, 1. So it has a 1 at the top in the first term and a 1 in the last term and zeros in the middle. And then I multiply out by this rotation matrix. And when I look at this, what happens is that because there's a plus here and a minus there, I get a 1 here, but the angle thing disappears. So this theta, so this rotation angle that I'm rotating about, just cancels. And similarly on the bottom row, it also cancels. And on the middle rows, I just get 0. So the state I get back when I do this rotation on both qubits is exactly the same state that I started with. So I try and rotate this entangled state of 2 qubits. Or if you like, if I think about the Bloch sphere, I try and rotate it and it doesn't move. And it's kind of worse than that because you just can't even visualize this state anymore with a single. And it makes sense because these entangled states are essentially not factorizable. So I can't separate it into 2 things. I can't make 2 images of it. It's kind of one thing now. So I can't make 2 separate images, 2 separate Bloch spheres. It's now impossible. So in this case, we've seen if we try to rotate, nothing happens. And my Bloch sphere picture just doesn't work. So that's what they were getting at in these tweets, that I have to abandon the Bloch sphere now as soon as I go beyond 1 qubit because of this problem. I can't separate it into a Bloch sphere for each qubit. So we need a completely new way to visualize these quantum states. And you kind of saw a little bit of how people go about it with those quantum circuits, but they look very complicated, you know, and so there's a lot going on there, as we saw spheres and yeah, lines, circles, colors, and stuff like that. So I'm going to present the way that I've been working on this together with my colleague Nikola Sibulich. Now, our ideas aren't completely unique. We're not the only people that have thought about these problems, and I'll just highlight a couple of nice PhDs from former years. They do slightly different things to us, but it's along the similar lines. So the basic idea now then is to visualize somehow this state, and we can't separate it, so we've got to represent it by one thing. And the question is, what's that thing going to be? And we're going to use the density matrix. So actually this is a mathematical thing, but we're just representing it in a visual way, because when I have a matrix, it's kind of easy to draw that matrix in some kind of a visual way and do that rather than mathematics. So a big matrix with loads of numbers means not a lot. But if I show my matrix using color, then I can maybe understand things a little bit better. So we're going to use what's called the density matrix, which for a pure state I can write like this. And for this block vector, it looks like this. So it actually has the 3 components, u, v, and w of the block vector appearing here. And the x and y components appear on the off diagonals, and the z component appears on the diagonal. So that's basically what the block vector looks like. All of these u, v, and w are all real numbers, which is convenient. So we'll get complex terms in the off diagonals, but real terms here. And because of the normalization of the state, because I can't have a probability of more than 1, then all these numbers are limited to a range of 0 to 1 or 1 to -1. So I know the domain of all these parameters in my matrix, and so I can represent them using something like a color wheel here. So in the color wheel, this is the complex plane. So we represent phase as the color. So the real axis is red, minus the real axis is green. And then as we go around the sphere on the imaginary axis, plus imaginary is yellow and minus imaginary is blue. So those are the colors we'll see as we change the phase of our state. And then as we go towards the center, as we reduce the amplitude, I can make this bigger. Then as we reduce the amplitude, we go to white. So if you like the sphere, the color becomes transparent and we'll just see white. Okay, so let's have a look now at our picture that we showed before and show what happens when we do this Rabi oscillation again. So basically now we start to, so when we start, basically it's just the zero term is non-zero. So we start with all the population in the zero state. So in our matrix, we just end up with a red, so a +1 here, which is red. And then as we evolve time, we start to see some off-diagonal stuff. And everything's red, which tells us it's all basically along this real axis here. So because it's coming out to this x-axis, everything's nice and real, so it's all red. And then when we get to that point, all the terms are equal, and they're all 0.5 in this matrix. So when we're in this superposition, then if we keep going, we get to this point here, roughly at the bottom now, and now everything is in the 1 state. So we see it all down here in the matrix. And then we can come back again. And when we come back, we come up the back side. So we're coming on the negative side now, the negative real axis. And you see the off diagonals are now green as we come back. And so on. So now this color evolution now represents what we had before. But it doesn't give us anything new in a sense. So we're only going to start to see extra stuff when we go beyond the block sphere to more than 1 qubit. Again, we can do things like, so if I just show you here what happens with decay, then decay reduces the amplitude of these things. And you see basically it gets lighter in color. So particularly these off-diagonal terms, you see the green going pale as we make the system decay. Okay, so that's our new representation. We can rotate around the other axis. So this is a rotation around X. Similarly, and now you see the blue and the yellow that I mentioned. So now because we're going into the complex part of the block sphere, and then again, if I add decay, you see it'll gets a bit paler. So maybe along here, you see how it gets paler when I add the decay as well. Okay, and then here, just to show you a bit of this decay fact, this is a rotation around Z. So here you see that the actual, this stays the same color, but so you see these different colors here as you rotate around Z. And now when you add decay, you can see that really what happens is that the whole thing collapses in on the axis. So this is this decoherence process where these coherences, so the coherence of the state collapses. And it becomes more and more classical. And what happens in this density matrix picture is the off-diagonal elements decay, and you see they get whiter and whiter. So eventually I collapse onto the axis, and now the population is still there, but there's nothing on these off-diagonal elements. And what we've ended up with is a state called a statistical mixture rather than a coherent superposition. And that's the classical, moving back towards the classical world. When we interact with our environment, we destroy the coherence of the process, and this is decoherence, which is basically the leading limitation of why we can't build quantum computers yet, because quantum systems decohere and they interact with the environment. So this helps us to understand that process. Now we can go on to more complicated things. So now let's consider this 2-qubit system and see at this irrotationality of the Bell state, and how does that look in this system? So now we visualize our density matrix, and because we now have 4 states, our density matrix is a 4x4 matrix. So there are 16, so it's 4x4 now. And if we start off again in the 0, 0, it's just like before. we're up in this square up here and we see red. And now as we basically drive the Rabi oscillations, so if we start in 0, 0, we can drive Rabi oscillations into 1, 1. And you see now here I'm down in 1, 1. And then as I come, then I basically drive them back again and I end up back in 0, 0 again. So this is now a Rabi oscillation, but for 2 qubits. And so it's doing this RY rotation on both qubits. And this is doing it on not on the Bell state, but just on a product state. So I start in 0, 0. But now what happens if I go to the Bell state? So in the Bell state, we're in a superposition of 0, 0 and 1, 1. So we see stuff both here and down there. And then because of the way that the density matrix is constructed, we see these off-diagonal elements as well in the density matrix. And now we apply the time evolution. And you see now the magic is nothing changes. Well, it's kind of a boring thing, right? That nothing changes. So it's completely different to what we had before when we started in a non-Bell state, in a product state. Then we see all this dynamics, and then we put the thing in the Bell state and nothing changes. So it's a really dramatic effect. Now this is summarized in this. So so those are interactive plots, but often you want to show this in a different way where you can just show all the information in one plot. So what this plot shows is the time evolution along the horizontal axis, and then along the vertical axis, we show 5 different input states. So at the top is this 0, 0 state, at the bottom is the 1, 1 state, and in the middle is this Bell state. And then these are kind of asymmetric, something in between these product states and this Bell state. And then if you look at what happens here, you can see this is what we saw in the interactive plot, that we start up here in the top left, and then we Rabi oscillate to the bottom right, and then back again. And similarly, if we start here in the 1, 1, we go to the 0, 0, and then back to the 1, 1. But when we do this on the Bell state, when we start in the superposition, then nothing changes. So this irrotationality property pops out of this visualization of the density matrix in a very nice, clean way. And then once you've done that and you've made a little code to simulate this and make these pictures, then you can start to study other cases. And these were cases I didn't really know about when I started. So this is now a rotation around Rx. So it's not really changing a lot, but actually things change dramatically as far as what happens in the picture. So if we now look at Rx, and we've got this way of turning on and off dots, just in case the color doesn't work or you're in black and white or something. So I'll leave the dots on. So now if we look at what happens when we try to do an Rx rotation, that's just the Rabi oscillation. So the same as before, we go from 0, 0 here to 1, 1, just as before. But now if I go to starting in the Bell state, let's look at what happens. So that was the Bell state, but now when I try the rotation, so it does change. So dramatically it does change, and it's quite a dramatic evolution. So, and if I just show you what happens, at some point we get to this state where everything's in the middle. So we started in the 4 corners, and now everything's in the middle. And the middle corresponds to having a superposition of 0, 1 and 1, 0. So actually what's happened is we've gone from this Bell state called phi plus to this Bell state called psi plus. So we've oscillated between the 2 Bell states. So in this case, there is a rotation happens, but it's a rotation in the Bell basis between these Bell states. So it's not so the entanglement is preserved, but it's a different type of Bell state that you end up with. So this is the kind of thing that you can start to visualize in this way, but it's just being possible using block spheres. So looking at those Bell states is really my first example of why I think we need to do something like visualize the density matrix, and why I think it's helpful. Now I want to show you one more example, which is from my own research on Rydberg atoms, and hopefully I can give you enough information to make this sort of understandable. So the basic idea with Rydberg atoms is that they're very strongly interacting. So let's say they're very highly excited atoms. So what I would do is have, say, a ground state atom in this state 0 here, and then excite it to a Rydberg state, which we'll call R. Now, what happens is if I try to excite another atom to a Rydberg state nearby, there's a strong interaction called a van der Waals interaction. So it's just like the usual van der Waals forces, but it's now very, very large, because these atoms are very large with the electron very far from the core. So there's a massive shift in the energy. So when I try to excite this second atom with the same wavelength, it doesn't get excited because the energy to excite it is now something completely different. So the excitation of this second Rydberg atom is blocked. And we call this process Rydberg Blockade. And this is very useful, and it's the basis of how you would build a Rydberg atom quantum computer. So this is the core concept, if you like, of how you do quantum computing with Rydberg atoms. Now, if we write down a Hamiltonian for this system, so we're going to have essentially 2 qubits again, but now our states are 0 and R rather than 0 and 1. So the one state, we're just calling it R. And all the operators then will be 4x4 matrices. So the Hamiltonian for this system, where we try to drive population to the Rydberg state in both atoms, is written like this. And again, we have this Rabi frequency, which is trying to drive the population up. And then on the diagonal, we have this van der Waals shift. And the blockade condition is that this van der Waals shift has to be much bigger than the Rabi frequency. Now, if that's the case, then essentially this doubly excited state, which is RR, when they're both in the Rydberg state, just becomes impossible. So that's what we see there. If we've got one Rydberg atom, we can't have another. So RR gets completely decoupled. And then this whole part of the matrix, we don't need any, we can cut off completely. So we don't basically enter this part of the matrix, and we just have this 3x3 matrix. Those are the only 3 states involved. So let's look at what we can do with that. So we now just have these 3 states. We have 0, 0, we have 0R, and we have R0. Now, to understand what happens, we can do what's called a change of basis. We go into the coupled basis. And the coupled basis, we replace, well, we keep 0, 0 the same, but we replace these 0R and R0 by 2 superpositions, 0R plus R0 and 0R minus R0. And then you remember these were these Bell states now, actually. So these are these states where I'm sort of up, down, or down, up in superpositions of those cases. And then mathematically, to convert to this coupled basis, we can just write down a rotation matrix, which transforms the old basis into the new basis, and then work out our new Hamiltonian. And it looks like this. And it's actually nice and simple. It now has only one coupling, and it's this √2 omega between the 0, 0 state and this psi plus state. So what happens now, if I draw this diagrammatically, is that the RR state is become completely decoupled because it's shifted completely by this van der Waals shift. And then the only state we can couple to is this 0R plus R0, which is the psi plus, the symmetric Bell state. And we couple to it with an increased Rabi frequency of √2 times omega. So that's what happens in Rydberg blockade. So what does that look like if we try and image it now using our 2 density matrix picture? So this is the picture that I had at the beginning of my talk, and it's quite complicated, but I think for me it's very beautiful. I like it a lot, but partly because I understand all the things that it's telling me. So hopefully I've told you enough that you can see. So what we learned before is if I just start in 0, 0 and I have uncoupled qubits, so there's no interaction, no entanglement, then we see this Rabi oscillation between the 0, 0 and the 1, 1 and back to 0, 0. So that's what we were familiar with of just a product state of independent qubits. And this we could represent with 2 block spheres, just 2 independent qubits. But now when we turn on this interaction between the Rydberg atoms, things start to change. So already you see there's some nice colors emerging here. And all we have to do is go down to so this shows the evolution as we crank up this interaction between the Rydberg qubits. And by the time we get to the last line, we're in this what's called the blockade regime, where these interactions are dominating over the driving of the laser. And now what you see here, if we compare, say, this column here, you see that whereas, well, or if we compare this column here, so whereas before we went to the RR state or 1-1 state, now when we add the interactions, the blockade means we don't go to RR anymore. That's completely blocked, so that's Rydberg blockade. And you see that this happens all the way along. So the point I made about we can remove these terms in the matrix and go back to a 3x3 system, we see that happening. So all the dynamics now happen in the first 9, this little 3x3 block of the matrix. There's nothing going into the bottom line or the line over on the right here. Now the other interesting thing that we see here is that we go to this state rather than going, we go to this block, this square block. So most of the stuff's 0 except for in this square block here. And if you remember when we looked at the Bell state, we said this term in the middle, this is this psi plus state where I just have a superposition of 0R plus R0. So that's what I showed you in the mathematics, that now we Rabi oscillate between 0, 0 and this Bell state psi plus. So we create entanglement just by this blockade process. We create entanglement directly, which is a nice feature of Rydberg blockade, that you can engineer these entangled Bell states very simply just by driving both atoms with a resonant laser. Now the other thing you see here is you see that everything happens much more quickly. So before we had to be over there to get back to the 0, 0, but on this lower plot we're already back to 0, 0 by this earlier time here, and that's that root 2 that I showed you on the previous slide. So remember that basically the Rabi oscillations are in. The Rabi frequency is enhanced by this factor of root 2 when we drive to this Bell state. So basically all the nice features of Rydberg blockade are in this diagram, and it just looks so nice that I like it a lot. So that's kind of the main point I want to get across with this quantum semiotics, that it gives us a new way of looking things that we're familiar with mathematically, but this diagrammatic representation gives us a new way of looking at it, and we can look for patterns. And there are many, many examples, so I've only had time to cover 2. This is a much more complicated thing. So this is basically what's known as the quantum Fourier transform. So now I have many qubits, I have big matrices, I look at different initial states, and then I look at what happens at various times in the circuit, and you get all sorts of patterns emerging. Now, this is kind of a new language in some way, so it's a new way of looking at things, but quantum itself is a new language, so we have to learn it. So what we've done is converted the mathematical language into a visual language, and just like we learned about maps and how to recognize a river from a road, we have to look at these pictures and learn how to recognize entanglement from product states. So there's in a way, there is a learning curve to all this, but I think it's perhaps a useful one to embark on. Okay, so that brings me to the end of the talk, and I want to just summarize the points I've tried to make. So Feynman told us that nobody understands quantum mechanics, and maybe we shouldn't worry about it, but yeah, I think we need to worry about it. And what we really need is that we need better tools to visualize quantum mechanics. And I've given one possible suggestion of how we might go about that. There may be others, there may be better ones, so maybe you can come up with a better one. The way I've shown you is we've chosen the density matrix. The density matrix is nice. It contains all the information about the state, including decoherence, coupling to the environment. It's scalable to n qubits. So it's kind of an obvious choice. Now, what we can say about this is that once we've made this visualization, once we can visualize our quantum states, we can turn quantum mechanics into some kind of image recognition task. And I think there's a broader picture there that I'm hoping that can be developed, where we basically combine all the current really exciting hot topics, where we say basically quantum computing, image recognition, machine learning, artificial intelligence, neural networks. We combine all these things into one topic. So we think of quantum algorithms as an image recognition, or we develop neural networks to develop quantum algorithms in some sense. So that brings me to the end with a sort of big vision for the future. I'd like to make a particular thanks to my colleague Nicola Sibulich, who's allowed me to make all these wonderful plots that I've shown you, and do things like these nice animations. So this just a little thing on to finish off on the Wigner function, and to show you the kind of things that we can do and include in talks. So I'll finish there, and I'm very happy to take questions, I guess, if you have questions. Thank you.
Yeah, thank you, sir, for your wonderful presentation. So we have got few questions in comment and in inbox. So if you allow, we can start our discussion session.
Yep.
First question. No, I can. Okay, manage. No problem. The first question: what is the block sphere?
Okay, so the block sphere is a way of representing the state of a two-state system in quantum mechanics. So basically, there are two free parameters, and then you represent those two free parameters as two angles, theta and phi, and then those two angles map into a point on the sphere. So it's really partly taking the mathematics and then trying to create a visualization out of that mathematics. So given that you have 2 degrees of freedom, and then you can map those 2 degrees of freedom into a point on a sphere. I don't know if people have heard of also the Poincare sphere. So the Poincare sphere is an equivalent for the polarization of light. So if you want to learn more about that, just look at the Wikipedia pages on block spheres and Poincare spheres. They've got very nice descriptions.
Thank you, sir. We have another question. So what is the 2-qubit operator?
Yeah, so when I basically an operator is something that changes the state of my quantum system. So if I have just 1 qubit, then I would apply an operator. Say I want to change the state. So I have 1 qubit, it's in state 0, and I want to now change that state to state 1. Then I would apply an operator, and that would be a single qubit operator, because I have 1 qubit and I apply it to 1 qubit. But if I have 2 qubits, then I have to build operators that act. I could have an operator that just acts on 1 of the qubits or the other qubit, but I could also have operators that act on both of them. So actually the example that I showed is just that I have let's say I have 2 atoms, and I shine a laser beam at both of them in the same time. How do I describe that mathematically? I describe it with a 2-qubit operator. I mean, it could be that they both do the same thing, but when they're entangled, I really have to describe that as a 2-qubit in terms of the 2-qubit states.
Okay, thank you. We have another question in the comment section. So first question, comment is, can we view quantum field theory from a semiotic perspective?
Yeah, I mean, in some sense, I guess you would say that Feynman diagrams is, I mean, it's maybe it was an example I hadn't thought about, but it's a great question, because I think, yeah, Feynman diagrams are kind of a great example of quantum semiotics, and maybe I'll put that in the talk next time.
Okay, thank you, sir. So this may be the last question. So is at every small distances of the order of the Planck length, our mathematical model of space-time as a continuous classical manifold untenable?
Sorry, I didn't quite understand what the question was, but
Okay, I can add the question here.
Okay. Yeah, so at very small distances of all are mathematical models of space-time as a continuous classical manifold on. Well, I mean, it's a good question. I don't know the answer to it. I mean, the question is that do we have to I guess it's a quantum gravity question. Do we need to quantize space? I think it's an open question. So I'm not an expert on quantum gravity. I mean, I know there are various theories. Because I'm an experimentalist, I tend to not believe anything unless it's testable experimentally. So so I would say there are theories of quantum gravity. There are various theories. People have different opinions. And until there's an experiment, I think we just don't know what the right answer is.
Sir, thank you for your wonderful presentation and exciting discussion session, sir. As the main aim of our program is to motivate our students, and as you have explained the quantum semiotic in new things and new research, so I think many of our students will be motivated, and maybe they feel interest in this new research and will join in this new research field. And that is also our aim, to motivate in research our student. So thanks again for helping us in arranging this webinar, and hopefully in near future we can arrange another webinar with you. And after the COVID, definitely we can invite you for a face-to-face session to visit our beautiful country. So thanks, sir,
Thank you
for
very
giving
much.
me this opportunity. Bye, sir. Have a
Thank
nice
you.
day.
Goodbye. Bye, everyone.
Bye.